Hello there, welcome back to Differential Questions by Alexander. All right, so today we're going to continue talking about undetermined coefficients, and specifically I want to mention something about linear operators. So today is just about linear operators, and what I mean by that is the following. Previously, we had dealt with the equation of this following type, where in front of the y prime, and in front of the y double prime, you only had numbers, and then you had some function g, which was a polynomial, an exponential, a trig function. And in the previous video, we saw that in order to solve this equation, we first have to find the complementary solution. So that was like the first step. The second step, or the second major step, was we'll find the particular solution. But to find the particular solution, we had to make a guess. Okay, we had to just make a guess and say, well, the particular solution is going to be of this format. And so it seems a little odd that we just are making a guess. And so what we want to do is, how do we know to make the correct guess? Or like, how do we come up with the specific good guess? And so that's the purpose of this video and then the next video. In this video, we're going to talk about operators. This is an O in the very beginning. We're going to talk about operators. And what we want to do is this, okay? We want to change this equation, which is a calculus question. This is a differential equation, which think of it as being a calculus question. We're going to change it into a language called operator, and then we're going to get an operator equation. All right, so that's the purpose of today. And we are going to focus on the idea about operators. So let's do this translation from calculus to operators, and then I'm going to explain three types of operators. All right, so the first thing that we need to do is we need to rewrite the equation. Instead of using the prime notation, we're going to use the Leibniz notation, which just means this other notation with the dy dx and then d square y dx squared. This means the second derivative and the first derivative. And what we're going to do in the next step is we're going to kind of peel off the y from the operators, from the differentiation. But they mean the same thing. And the instructions are telling us differentiate twice the y function and then differentiate once the y function. And so in this format, we can see that every single term has a y. And so we think of factoring out the y. And so that's what we have here. And so now this thing in the red box, and actually let me put this in the blue box now. So this blue box, think of this as being the set of instructions on what to do to the function y. Okay, and I put a dot here not to indicate that this is a multiplication. This is just to separate the blue box with the y. So ignore the little dots. So the set of instructions is everything inside the box. And then this is what you're supposed to do to the y, and then the output is supposed to be the g function. So now we are ready to change our original differential equation, which is in the calculus language. We're going to change it into the operator equation. And so this is what we mean. So this blue box that we had written down, this is going to be your L. So what we're saying is this: L is equal to this 4d squared dx squared plus 7d dx plus 3. So L does not have a y in there. Okay, so this is your operator. And instead of writing down this lengthy 4d squared dx squared plus 7dx ddx plus 3, instead of writing all that down, we sometimes give it a name, and so we just call it the L. So L is just the name of the set of instructions. And so this is us changing the original calculus equation into an operator equation. All right, so that's what we mean by changing the differential equation into an operator equation. And so our focus now today is going to be about this operator else. Okay. All right, so now in the previous example, I had specific numbers for the A, B, and C, but now I'm going to repeat the story, but just with the A, B, C. A, B, C are just any numbers that you can think of. And so again, I'll repeat the story. And so we change the prime notation into the Leibniz notation, and then we kind of peel off the y's, and then when we do that, we can factor out the y out, and then this thing in the blue box, that is going to be our operator L, and so that is going to allow us to write the equation in this format. So sometimes we write down L of y, so we think of L as being a big function, and then the input is the function y. And again, L is this thing in the blue box, so I won't rewrite it out. I'm going to highlight. L is this entire blue box, and then L is your set of instructions. And in this case, there are a set of instructions on how to differentiate and add things together after you apply it to the y. And so we change the general differential equation into an operator equation. And again, our focus is on the operator L itself. But not just this. So this is the general operator L, but now we're going to move up a little bit, and then we're going to talk about different operators. In particular, we're going to talk about 3 types of operator. So let me talk about well, actually, before we do that, here, I do want to show a little bit of notation. Sometimes we change the notation even further. So we sometimes write down this as d dx squared plus b d dx plus c. So sometimes we write that down, and then we even go further. We write down d, capital D, to stand for the derivative action. Okay, so here the d represents the d over dx. Okay, so we are changing notation, but we're still talking about the same operator L. And then we do this because we want to simplify our handwriting and like to see the bigger picture. We don't want to get lost with writing down this d over dx over and over and over again. All right, so just a small comment, and then you'll see this often throughout. All right, so just a little bit of definitions for the operator L. So L could be any operator, and then we are going to say that an operator annihilates, or another word for this will be eliminates or cancels. So the operator L eliminates a function y if whenever you apply the L operator to the y, the output is equal to 0. Okay, so for example, if I told you to, so suppose that you have this second derivative operator, and then suppose that you apply this to the function, let's say 3x. So if you apply this second derivative to the 3x function, what is the output? The output is equal to 0. And so in this case, the L operator, which is the second derivative, annihilates, cancel the y function, which is the 3x, okay, because it satisfies this equation. We plug in the y function into the operator, and then the output is going to be 0. When that happens, we say that the operator annihilates or cancels the function y. Another property is about linear operators. Okay, so we're putting an extra adjective here, and linear operator means the following. Suppose that you have two functions y1 and y2 that are annihilated by the L, which means that L of y1 is equal to 0 and L of y2 is equal to 0. So suppose that you already know that for the y1 function and the y2 functions. And what the statement here is saying is that if your operator is linear, then you can actually make any linear combination of the y1 and the y2, and you apply the L, and then the output is going to be 0. Okay, so this is a property that we are going to use heavily. So just remember this property about linear operators. Okay, linear operators, and we are going to be dealing only with linear operators in this section. All right, so that's some questions related to different operators, and here let me just write down some few details here. So the operator is the derivative operator, and then we, instead of writing down d over dx all the time, we want to give it a name, and so we give it the name L. And so we want to show that this operator annihilates the function 1, but it does not eliminate the function x. And so what that means is the following. So when you plug in the 1 function into the operator L, this is just telling us back in calculus, this is telling differentiate the function 1, and so the answer is 0. So check, it does annihilate the function y. Now do the same process for the other function. So the operator is d over dx, and then we are going to apply this to the function x. And what is the derivative of x? It is equal to 1. So this is not equal to 0, and so therefore the operator L does not annihilate the function y equal to x. All right, so just to get comfortable with the idea here. And now the property on the bottom says the following. So the operator annihilates any combination of this format or any function of this format, and then this can be seen in the following way. So C0, this is the same thing as d over dx multiplied acting on the C0 times 1. And then a property of the linear operator is the following. If you have a number multiplied by a function, you can factor out that number, and so you'll get a C0 on the outside, and then you have the d over dx acting on the 1, and we know that that is equal to 0, and so the whole thing is equal to 0. All right, so the operator L annihilates anything that is a constant function. All right, so that's the first example. Let's go for a second example. Now we're gonna move up a little bit in the complexity. And so what we're saying is this: the operator is its entire thing. This is technically the second derivative operator, and then we're going to call it the operator L. So we just give it a name to the entire blue box. It's called the L operator, and then we want to show that this operator annihilates or cancels out the one function and then the x function, but not the x squared function. And so just think about it. So this is just saying the second derivative of the one function, for sure it's 0, and then the second derivative of the function x also is equal to 0. But now when you do the, and actually let me do the steps here. Okay, so this is applied to the x squared. What this means is you're going to apply this derivative operator twice, and you're going to apply it to the x squared. And so let me put this in a red box because that's the first step that we're going to do. You already know the answer, but I want to show the steps or the idea about the operators. So this is going to be 2x inside the red box. And now if we differentiate one more time, then we're going to get what? We're going to get 2, which is not equal to 0. Okay, so this is not equal to 0, and therefore the operator L does not annihilate or does not cancel out the function y is equal to x squared. Okay, and I'm showing this extra work just to get comfortable with the idea that we're moving from basic calculus, we're moving to the idea of operators. And so the operator that we have here in the beginning, this is the second derivative operator, which means you apply the d over dx twice. And so that's why I did the steps to show you that. Now, here on the bottom, we have the same operator, and then we want to show that it also annihilates the combination of these two functions. So we already showed that it cancels out the y function, y is equal to 1 function, and then the y is equal to x function. So that means that the operator L will cancel out any linear combination of the y1 and then the c2. And actually, let me write it out this way. So this is L acting on C1, and then this is the number 1 plus C2 multiplied by the X, and this is C1 L of 1 plus C2 L of X. And what do you know about the individual L acting on the 1 function is equal to 0, and L acting on the X function is also equal to 0, and so the whole thing is equal to 0. And so therefore L acting on the linear combination of the two functions from the very beginning, so y1 and y2, L acting on that will also be equal to 0. All right, so this is a property of the linear operator. All right, so now the same thing, so we're just repeating the story, but we're adding a little bit. But I want to kind of see the pattern here. I want you to see the pattern. So now we have the operator, which is the third derivative. And then you could have guessed that this is going to annihilate 1x and x squared, but it does not does not cancel out the x to the third power. Okay, so you can show that, but I want to kind of focus on the picture here. And now, so now suppose that you already check those three functions are eliminated by the red operator, then that means that the red operator, which is the third derivative, if you apply it to c0 plus c1x plus c2x squared, this is also going to be equal to 0 because individually you already checked that the red operator cancels out the function 1, the function x, and the function x squared, which are the linear combinations here on the bottom. All right, so now let's make this a little bit more general. So just going up one more level, you would have guessed. So now the question is more specific. Does the operator L in red, does this cancel, I misspelled here. So does this annihilate or does this cancel out the polynomial 4x to the 3 plus 4ax plus 92? And the answer is yes. Okay, and the reason is because L eliminates. I usually say eliminates. I don't. But technically we should say annihilates. So the L operator eliminates the functions 1, x, x squared, and also x to the third power. And notice that technically this is what we have. So we have a 1 there, we have an x, and then we have x to the 3. So we have a linear combination of the 1, the x, and the x to the 3. And so therefore the L, when you apply this to the p function that's given above, this will be equal to 0. Okay? Because we know that the L specifically given by this operator, does cancel out the 1, the x squared, and then the x to the third power. We didn't use the x squared in this case, but just extra information. All right, so now what about the more general situation? Okay, so now we can kind of say this a little bit more generally. So we have this operator, which is the nth derivative, and we can say that this nth derivative eliminates all the functions with x to the power, but the power has to be less than n. And notice that this is the same thing as x to the 0. This 1 is the same thing as x to the 0. And so we are just saying this, and I'll repeat this again. This eliminates x to the k, and the k can be starting from 0, 1, 2, all the way to the n minus 1. Okay, so that's what the statement is saying, and I've given you some examples to see how that looks like whenever you have a specific n value. All right, so that's the first type of operator. Now let's move on to the second type of operator, and here we need to first choose a number alpha, and alpha is going to be a constant, any number that you want to. And now the operator that we are focused on is on this type. Okay, so this is a new type of operator. This is the second type of operator. And so the question A is asking us to show that this blue operator annihilates or cancels out this function e to the alpha x. And what that means is this. We want to show that if we apply L to the function e to the alpha x, we want to show that this is equal to 0. So at the moment, this is a question mark. Okay, question mark. So that's what we want to show. And so specifically, we have this operator, the x minus alpha, and then this is going to be applied to the function e to the alpha x. And so now let's distribute. So this is going to be alpha x here minus alpha e to the alpha x. So now what do you know about the first derivative of the e to the alpha x? That's going to be alpha e to the alpha x. And now I'm going to copy and paste this second guy. So alpha e to the alpha x. And what do you know? They are the same term, and so the entire thing is equal to 0. So now this is us showing that the operator in the blue box operator cancels out the e to the alpha x function. Okay, and now the property on the bottom says the following. If you were to apply the same blue operator to the multiple, so multiply the e to the alpha x by any number, one of the properties of the linear operators is that if you have a constant in front of the multiplied by the function, you can factor that outside the operator, and so you will have the C0 outside, and then you have your operator, the x minus alpha, acting on the function e to the alpha x. And what do you know about the operator acting on the e to the alpha x? We know that that is equal to 0. So C0 times 0 is equal to 0. So this is us showing that you can actually, not as soon as you know that a operator cancels out a function, you can actually multiply that function by any number, and so the operator still cancels out that new function. All right, so that's our first example. All right, so now we're going to move up one level, and the difference between this problem and the previous one is that now you have a second power here. So the operator, you have to apply it twice. Okay, so this is going to be a little bit lengthy, so let me do the work for this guy. Okay, so it might be, so the first one would be, the first function is a little easier, but what this means is the following. We need to show that, and let me put this in blue, that way to be consistent. We have this operator, and then this is twice, so that means we actually have two copies of this operator. And then we want to apply this blue operator, including the 2. We want to apply this blue operator to the function xe to the alpha x. Okay, so what that means is we first have to apply one copy of the operator to the function. So this is this red box. This is what we have to do first. Okay, so I'm going to distribute. So this is d over dx minus alpha. And this is going to be d dx acting on xe alpha x minus alpha xe to the alpha x. And so let me put the red box just to indicate what I'm doing. I distributed the xe to the alpha x to the inside the operator. Now, here comes a little bit of calculus here. So we have to differentiate this thing in the smaller red box. So the thing in the smaller red box, we have to differentiate this function, which is x multiplied by e to the alpha x. And when we do that, we have to use the product rule. So let me put that in gray. That way I kind of separate the lines. So notice that we haven't done anything with this operator on the outside. And so let me put this. And so this is going to be the first one times the derivative of the second one, which gives him an extra x, plus the second one, alpha x, times the root of the first, minus the, just copy and paste the last term. All right, so again, let me put the red parentheses, red brackets, just to indicate what we have done. Okay, so we differentiated and we have to use the product rule. But now, what do you know about inside the red square bracket? The first term and then the last term, they cancel out. And so let me go down to the bottom, So this is going to be equal to, so again, we haven't done anything with this operator in the very beginning. And then what this is saying is that we only have e to the alpha x. The operator acting on e to the alpha x. But what do we know about this operator in the black box now? What do we know about this operator in the black box acting on the function e to the alpha x? We already showed in the previous example that this is cancelled, and so this is equal to 0. And so what we're saying is this: the operator L, which I'm going to put a black box here now. So the operator L in the black box, when you apply it to the function x e to the alpha x, the output is going to be equal to 0. The output is going to be equal to 0. So this is us showing that the operator L annihilates or eliminates or cancels the function x e to the alpha x. You can also do the same thing for the other function, just e to the alpha x. That one's a little bit easier. All right, so for the part B, it's the same thing as before. So I'm just gonna write down the general idea here. So you have two functions in the very beginning. So you have the y1 and then the y2 function. And what this is saying is the following. So L, whenever you apply L to the individual function, so C0 y1 plus C1 y plus C0 y0, well, different labels, okay? So y1, y2. So that means that you can take out the functions that's constants, and then you have the y1 plus C2 or C1, whatever you want to call it, times the y2. But what do we know about L acting on the individual functions that we have on the very top? So those are equal to 0, and so the whole thing is equal to 0. So this is just the general idea. Again, I want to emphasize that for the linear operators, we have this property that you can split up the plus sign. L can be applied to the first term and to the second term, and not only that, you can actually factor out the constants out. All right, so that's another example for the second type of operator. And now I'm going to just give you the information here for this one. So here we have the operator, and I'll put this in the blue box, but now the power is to the third power. Okay, this is to the third power. And what we're saying is this blue operator is going to cancel out functions of the following format. So xk e raised to the alpha x. And then the k here can be either the value 1, 0, 1, or 2. So technically the first function that we have here, this is the same thing as x to the 0 e to the alpha x. So that's why I'm saying that we only need to remember this format. So this blue operator, which is your second type of operator, this blue operator cancels out functions of this format: x to the power k, e to the alpha x, but the k can only be a power less than the 3. K has to be a power less than the 3. All right, so that's a 1, that's a 2. Now I want to make this a little bit more general. We bump up a level, and so again, the same type of operator, but now this is the power 4. And so we see that this is going to cancel out x to the power k, e to the alpha x, and then the k can be any value 0, 1, 2, or even 3, but not the 4. Okay, so remember, this is the same thing as x to the 0 power. All right, so these are the functions that are canceled by the operator L. And one other thing that I want to mention is these functions are linearly independent. These 4 functions are linearly independent. So you have to remember what that means. the easy check would be to check the Wronskian. Yeah. So these are four linearly independent functions that are cancelled by the blue operator. So now let's move up one more level, the more general level. So first you have the same operator, but now this is the power n more generally. And so we said that this is going to cancel functions of this format, which is x to the k, e to the alpha k, where the k can be technically x to the 0, a 1, a 2, a 3, and up to the power n minus 1. That's what the k value can be. So this is the type of functions that are cancelled by the blue operator. So again, this is the second type of operator. And now I have one more type of operator that I want to talk about. But to do so, I need to review a question that we have done already. Well, we have done this type of question before. So this is a homogeneous linear differential equation with constant coefficients. And so we're going to solve this equation. So this is actually not it's not actually an operator question here. This is just a question that we have done before. But in order to give you the third type of operator, I want to show you where it's coming from. Okay, so this is where it's coming from. We have this differential equation, and then we want to solve the differential equation. So do you remember what we have to do to solve a homogeneous second order linear differential equation? Well, we are going to assume that the solution, is of the following format, e to the mx. Okay, so we assume that the solution is going to be e to the mx, and at the moment we do not know what the m is equal to. So that actually is the question. And what we're going to do is we're going to plug it into the differential equation, and then we do some algebra or some calculus in algebra, and then we're going to get the auxiliary equation. So the auxiliary equation becomes m squared minus 2 alpha m plus alpha squared plus beta squared is equal to 0. Okay, so this is called the auxiliary equation, and should be a review. All right, so now how do we solve this algebra equation? The question still is, what is the value for m? So now this is an algebra question, so this is a quadratic equation with the variable m. And so now we have to identify the a. So a is equal to 1, the b is equal to -2 alpha, and then the c is equal to alpha squared plus beta squared. So I'm using a, b, c for my quadratic formula. So I won't rewrite it, so I'm just going to use the quadratic formula. And so the quadratic formula says that this is going to be -b, so 2 alpha plus or minus square root of the b squared, which gives us a 4 alpha squared minus 4ac, and then this becomes alpha squared plus beta squared. So I'm just using quadratic formula here, nothing complicated, divided by 2a, so this is just a 2. Now I need to simplify this a little bit, so this is going to be 2 alpha divided by 2. And notice that when you distribute the -4, the -4 with the alpha square cancels out with the +4 alpha square. So you only get the following. So let me write down the details. So this is plus or minus, and then you get square root of -4 beta squared divided by 2. All right, so now we need to simplify this a little bit more. So this is alpha plus or minus, and then the 4 can be taken out of the square roots, and then the 4, when you take it out, becomes a 2, and then that cancels out with the 2 on the bottom. And then we have a negative beta square inside the square roots. But now what we're going to do is we're going to take out or eliminate the square root of -1, which gives us a I. Okay, so this is going to be I beta. So that's what you get after you do a little bit of algebra, and so you get alpha plus or minus I beta. So what was the original question? Very lengthy, right? So very lengthy, but what was the original question? The original question is, what is the solution to this differential equation? So we do all this, we basically came up with an algebra question in blue, and so we have the answer for the m. Okay, so m is equal to this blue number, alpha plus I beta. But now what we want to say is, what is the solution to the homogeneous equation? And so I'm going to write down, and then previously we talked about the format here. Whenever we have a complex number alpha plus I beta, the solutions are going to be y1 is going to be e to the alpha x cosine beta x. and y2 is going to be e to the alpha x sine beta x. So this should be, again, a review of what we have done so far. All right, so those are your solutions to your linearly independent solutions to your differential equation. The question was asking us what is the general solution. So the general solution will be the linear combination of these guys. So this will be C1 e to the alpha x cosine beta x plus C2 e to the alpha x sine beta x. All right, so that will be the general solution to the red homogeneous equation. All right, so that's a review, but now here comes the thing that I want to communicate. So I did this problem because I want to show you the following. So notice the format of the differential equation. You have the minus 2 alpha, and then you have the alpha squared plus beta squared. And now we are saying that the solution to this differential equation are given by the thing on the bottom. This is general solution. But we want to kind of focus on the linearly independent functions. So put this in red. So y1 and y2 are your two linearly independent functions that are solutions to your differential equation. Now we're going to switch the story around. Okay, so right now this stuff in red, think of that as being the calculus version, the differential equations version. But now we're going to change this into an operator language. So what we're saying is the following. Now look at the operator, which does not have a y. We have this operator, and what we're saying is this: the operator in red annihilates or eliminates these two functions. So y1 given by this, and y2 given by this other one. That's the purpose of showing the previous exercise. Okay, it is a review, but I want to kind of say the bigger picture now is the operator cancels out these two functions. Okay, so these are your two linearly independent functions that are canceled by this L operator in red. All right, so now we're going to move up one more level. So now suppose that you have the red operator from before, but now you are going to square this. Okay, so now notice that the two functions on the red box that I'm putting here on the bottom, these are the original two functions from before. But now since you have a power 2, you have two more functions that are also eliminated, and then these are going to be x multiplied by the e cosine, and then x multiplied by the e sine. Right? We won't check this because it takes a long time to just solve the original problem. So now, what if you have the operator? Again, this is the same operator from the beginning, but now we have the power 3. What type of functions will be eliminated by this operator in red? The entire red operator. Okay, so the entire thing. So we are going to get the same functions from before, but we also add this extra line on the very bottom, and then this is x to the power 2, x to the power 2. Notice that 2 is 1 less than the power that is given here. So 2 is 1 less than the power given to you. And so what we're saying is this: whenever you have an operator of this format, you should be thinking, well, if you have this format, then the functions that are eliminated by that L operator are going to be x to the k, e to the alpha x, and either cosine or sine of the beta x. And now the restriction is that the k, in this case, will be 0, 1, 2, but not the 3. Okay, k will be 0, 1, and 2, but not the 3. And notice again, I'm going to make a little comment here. This is the same thing as x to the 0, because x, well, anything to the 0 power is the number 1. So technically, this is the format of the function that we want to memorize. So this is the third type of operator, and then these are the type of functions that are eliminated by the third type of operator, where either you have a cosine or you have a sine. So let me just erase the sine just to make it more clear. So this is one type of functions, and the other type of function is replacing the cosine with a sine. So now let's move up one more level. I will make it general, but suppose that you have now a power 4. So this is your red operator, including the fourth power. So what are the functions that are going to be eliminated by this operator? So you would guess that they are of the format x to the k, e to the alpha x, and let me just write down sine in this case, but you also have the cosines. So x to the k, e to the alpha x, cosine of beta x. But now the power k, what are the possible values for k? Well, they are going to be 0, 1, 2, and 3, and you stop there. All right, so how many functions do you have? You have 8 functions. and you have, and these are 8 linearly independent functions that are eliminated by this red operator on the very top. All right. So now that we have covered the different type of operators, now I want to ask questions about if you have a function. So this is not a differential equation. This is just a function. So let me put this in a different color. Let me put this in purple. So if you just have a function, the question here is asking us, I want to choose the numbers for the n, the alpha, and the beta. I need to figure out the values for n, alpha, and beta, so that the operator, this very complicated operator, cancels out the y function. So what do n, alpha, and beta have to be? What do n, alpha, and beta have to be? Well, in this case, this is the power on the x, so the n has to be 1 bigger than the power. Okay, n has to be 1 value bigger than the value on the x. Okay, so that is coming from the x, and now the alpha, it refers to what is on the exponential. Okay, so this is the -2, and that refers to what is on the exponential. And now the 7 is going to give us the beta. So 7, which is matching here also, that is going to be our value for beta. So that means that we can figure out the operator L that is going to cancel out the y function, and then the operator is going to be given by this, the x squared minus 2, and I want to just write down the value exactly as it is, that way you can see where it's coming from. So plus alpha squared, which is a 4, plus beta squared, which is 49, and then the whole thing raised to what power? It's going to be raised to the 3rd power. So the operator that cancels out the y function from the very beginning, this operator in the red box, this is going to cancel out the function on the very top. This is one single function, and then we wanted to figure out what is the operator that cancels out that function. So we have to figure out the n, the alpha, and the beta. So let me give you just another example of this type, just to test. All right, so now I'm going to rewrite this function slightly. Okay, so this is the same thing as 3x to the 0 e to the 0 cosine 7x, and again 8x to the 0 e to the 0 sine of 7x. Okay, so the reason I wrote it out this way is because now you can kind of figure out that we are able to identify the n, the alpha, and the beta. So what do the n, alpha, and beta have to be here? So the n is going to be 1 bigger than the power on the x, which it has to be a 1. So the x has the power 0, and so the n has to be 1 value bigger than that. So it's going to be n is equal to 1. The alpha is the number on the exponential, and technically there's a 0x there, a 0x there, and so alpha is going to be 0. Beta is going to be what? It's going to be the number inside the sine and the cosine, which is a 7. All right, so we have all the values so that we can write down the operator that is going to eliminate the original function. And so this is going to be d dx squared minus, actually the alpha is 0, so we won't even write that down. Okay, well, actually let me just write it down, that way you know where it's coming from. And now this is going to be plus 0 squared plus beta squared, which is a 49. And then this is to what power? Power 1. And so if you simplify this a little bit, then you'll get the following: d dx squared plus 49. Okay, so simplify everything, and you get this to be your operator. And then this, I'll put it in the red box. And so this operator in the red box is the operator that cancels out this function in the very beginning. All right. So that's how we play the game. Okay. So now let me give you another test question. So a little bit faster now. So we can already identify that the n has to be 1. The alpha is going to be 0 because there is no exponential, there is no x in the formula. And now the beta that we have is going to be a 5. And if you look at the work from before, you can automatically say that this is going to be d dx squared minus 25. Okay. Minus 25. So that's after you see the pattern from before. And we're saying that this operator in red is the operator that cancels out this function in the very beginning. So L, when you apply it to the y function, this is going to give you 0. And you can check that if you wanted to. All right, so now another test question. This is a review from the other type of operator. So suppose that you have this function, which is just x e to the alpha, e to the 4x. And so in this case, we need to identify the alpha and then the n. Okay, so the n is probably the easier one. N always refers to the power on the x. Okay, so x has a power 1. And so that means that for this specific problem, the n has to be same format as before. This is 1 bigger than the power on the x. So n has to be equal to 2. And now what about the alpha? The alpha is the number on the exponential, the power on the exponential. And so alpha is going to be equal to 4. So that's all you need to know for this. This is the second type of operator that we talked about. And so this operator is going to be the dx minus 4, and then this is going to be to the second power. So this operator that we just wrote down, and I'll put this in the red box, this operator is the operator that cancels out this y function in the very beginning. And again, that means that if you apply the operator to the y function, the output is going to be equal to 0. All right, so I have a few more questions, 2 more questions. So same game as before, and now let's figure out what the n is going to be and what the alpha is going to be. So n is going to be, look at the power on the x, the n has to be 1 bigger than that, so it's going to be a 3. Now what about the alpha? The alpha is the number on the exponential, which is an 8. Okay. So now the operator that we care about is the following. So this is going to be d dx minus 8 raised to the third power. And so again, this is the operator. This is the operator that eliminates the function in the very beginning. Or we should also say annihilates the function y. One more example. This is a little bit more involved. Okay, so now this function has 3 pieces to it. So we have, let me write it out this way. Let's start with this part here. So x to the 6. Okay, so let's separate the problem into 3 parts. So let's look at the blue function. And then the question is, what is the operator that annihilates the blue function? What is the operator that annihilates the blue function? Well, this is the first type of operator, which is the easier type of operator. And this is going to be the differentiation 7 times. So you differentiate the blue function 7 times, the output will be 0. So this blue operator on the bottom, this is the annihilator of the blue function. Now let's move on to the next term. So the next term is x to the 7 e to the negative 2x. All right, so here we have to identify the n. So the n is going to be equal to 8. Alpha is going to be equal to negative 2. And so the operator that we care about is the following. So it's going to be d dx plus 2. And then this is going to be raised to the 8th power. Okay, so this is the second type of operator that we talked about. And so this purple operator is the operator that eliminates the purple function. Now let's move on to the third term. So the third term is a little bit more involved. So we have to identify the n. So the n is going to be 6 because it has to be one value bigger than what you have the power on the x. Then we also have to identify the alpha. The alpha in this case is equal to 4. And then the beta in this case is going to be equal to 3. And so the operator that annihilates this red function is going to be, so I need to write this down a little bit smaller. So the derivative square minus 2 alpha, so 2 multiplied by 4, 2 alpha d dx plus alpha square, which is 16, plus beta square, which is a 9, and then the whole thing raised to what power? The power 6. All right, so what we have done is we have 3 functions being added to each other. So we have the blue function plus the purple function plus the red function, and we individually found out what is the operator that annihilates each individual function. And so now the question is, what is the operator that annihilates the entire thing? So the operator that annihilates the entire function. Okay, so what if you want to consider the entire function, and then you want to know what is the operator that cancels out the entire function? Well, the answer is very simple. Once you find the individual pieces, you just multiply them out. So technically we're done here. So we just put multiplication here, and that is the operator that cancels out the entire function y. So let me just write it out just one more time, just to put it in one single color. And so this is d dx plus 2 to the 8th power, and then we're going to multiply this by d dx squared minus 8 d dx, and then this becomes a what? 16 plus 9, that's a 25, and then this to the 6. So what we're saying is this operator in the red box in the very bottom, this operator is the operator that cancels out this original y function, which has 3 terms to it. And then to figure that out, you just look at term by term and then multiply the operators. All right, so that's all I have for this. Okay, so I hope that this is helpful. And remember, our goal for this video was to talk about the operators. And now in this case, at the end of the presentation, we were talking about what is the operator that cancels out specific functions. Now in the next video, we want to know how is that connected to the particular solution. So remember, in the very beginning, we said something about the particular solutions, and then we had to guess what the particular solution was. But now we talked about operators today, and then in the next video, we're going to figure out how the operators allow us to make the specific guess. Okay. All right, so I'll see you next time. Thank you for watching.